how the solar system was born from chaos 4.6 billion years ago. Before there was a sun, before there was an Earth, before there was anything you could stand on or point a telescope at, there was 4.6 billion years of nothing you'd recognize, just a cold, dark cloud drifting through the Milky Way, minding its own business. It had no reason to become a solar system. Most clouds like it never do. But this one did, and everything that followed, every planet, every moon, every comet, you, sitting there watching this right now, is downstream of what happened next. This is that story, told in order start to finish, the way it actually unfolded over the next 2 hours. We're not going to rush it, because rushing it is exactly how you end up with the cartoon version, a swirling blob that magically becomes 8 tidy planets in a montage. The real version is messier, better documented than you'd expect, and in several places still an open argument among the people who study it for a living. We'll walk through the collapse of the birth cloud and the isotope evidence for what may have kicked it off. We'll sit inside the protoplanetary disk phase long enough to understand the physics of why it flattened, and look at the actual disks astronomers have photographed around other young stars as living proof this isn't guesswork. We'll cover the genuinely unsolved problem of how dust becomes a planet in the first place. We'll follow the frost line as it splits the solar system into 2 fundamentally different building projects. We'll spend serious time on the moon, because the leading explanation for its existence created its own scientific crisis that took decades to even partially resolve. We'll look at the bombardment record written into lunar rock. And we'll finish with the giant planets themselves, wandering out of their birth positions in an episode of solar system history, so violent it reshaped everything past Saturn. Every claim in this video is going to be graded, out loud, as we go, well supported and broadly accepted, versus still actively debated among researchers. Both categories are part of honest science, and pretending otherwise would do this story a disservice. So let's start where the story actually starts, not with a bang, but with a slow, cold, patient cloud of gas that had been sitting quietly for a very long time before anything happened to it at all. 000 Prologue, a cloud with no plans. Picture a molecular cloud a few light years across, mostly hydrogen and helium, laced with heavier elements, carbon, oxygen, iron, silicon, that didn't come from the Big Bang at all. They were forged inside earlier generations of stars and blasted into space when those stars died. Every solid thing in the solar system, including the iron in your blood, is recycled stellar wreckage. That's not poetry, that's nucleosynthesis, and it's about as well established as physics gets. The pattern of elements we find in the sun, in meteorites, in your own bloodstream, matches almost exactly what nuclear astrophysics predicts should come out of the cores and explosive deaths of stars several times more massive than our own. Clouds like this are not rare. The Milky Way is full of them, some vast enough to birth tens of thousands of stars, others small enough to produce a single, unremarkable one. Most of a molecular cloud's mass sits at temperatures barely above absolute zero, around 10 to 20 Kelvin, dense by interstellar standards, but still thinner than the best vacuum we can create in a laboratory on Earth. What holds a cloud like this together against its own gravity, for millions of years at a stretch, is a standoff between competing forces. Gravity constantly pulling inward, and internal turbulence, magnetic fields and thermal pressure pushing back outward. For most of a cloud's life, that standoff holds. Star formation, on the scale of an entire cloud, is actually a slow and inefficient process. Only a small percentage of a cloud's mass typically ends up in stars at all, with the rest dispersing back into the interstellar medium or getting blown away by the very stars that do form. Our particular cloud sat in that quiet, stable state for some unknown stretch of time before the balance tipped. We'll spend the rest of this chapter on what tipped it, because the honest answer is that we don't know for certain. But we have real physical evidence to reason from, preserved, remarkably, in rocks that are still sitting in museum drawers and university freezers today. 435 Chapter 1 The Cloud Gets a Push. Supernovae, Isotopes, and a Cold Case asterisk. Gravitational collapse of a cloud fragment doesn't require a dramatic trigger. In principle, if a clump of gas within a cloud becomes locally dense enough on its own, crossing what astronomers call the Jeans criterion, the point where a region's self-gravity finally overwhelms the outward push of its internal pressure, it can begin collapsing under nothing more exotic than its own weight and a bit of bad luck in how the turbulence happened to arrange the gas that day. That's the boring, unglamorous, and entirely sufficient explanation, and it may be exactly what happened to the cloud fragment that became our solar system. But there's a more dramatic candidate that has occupied astronomers for decades, and it comes from evidence baked directly into some of the oldest solid material in the solar system. Calcium-aluminum-rich inclusions, or CAIs, found inside primitive meteorites, most famously fragments of the Allende meteorite that fell over Mexico in 1969, a specimen so scientifically productive that researchers still joke there's more Allende in laboratories than there ever was in the original fall. These CAIs are widely regarded, on strong isotopic and textural evidence, as the oldest solids that condensed in the early solar system, dated to roughly 4.567 billion years ago, with extraordinary precision using lead-lead radiometric dating. Locked inside them are decay products of isotopes that no longer exist in nature because they were radioactive with short half-lives. Meaning if we find their fingerprints today, those isotopes had to have been freshly made and delivered into the cloud only shortly before the solar system's oldest solids formed. The headline isotope here is aluminum-26, which decays into magnesium-26 with a half-life of only about 717,000 years, a blink of an eye on astronomical timescales. When researchers measure an excess of magnesium-26 in these ancient meteorite inclusions, in a pattern that correlates cleanly with how much aluminum was originally present, that's strong evidence that live aluminum-26 was mixed into the material before it solidified. Aluminum-26 is produced in exactly the environments you'd expect: the cores of massive stars, the winds of dying giant stars, and supernova explosions. Given its extremely short half-life, the aluminum-26 found in these meteorites essentially had to have been produced and injected into our cloud within roughly 1 million years of the solar system's solids forming, a genuinely tight window that points toward a nearby, recent, and massive stellar event. For a long time, the leading interpretation was a nearby supernova, a massive star, one of possibly several formed in the same star-forming region as the Sun's birth cloud, reaching the end of its life and exploding close enough, and soon enough, to seed the collapsing cloud with freshly minted isotopes while also potentially delivering the physical shockwave that helped tip the cloud into collapse in the first place. It's an elegant 2-for-1 story. The same catastrophic event that enriched the cloud chemically also gave it the gravitational nudge it needed. There's a second isotope in this story, and it's where the picture gets genuinely messier. Iron-60 decays into nickel-60 with a half-life of about 2.6 million years, and it is produced almost exclusively in the late stages of massive star evolution and in supernova explosions, unlike aluminum-26, which can also come from the winds of massive stars without an explosion at all. Early studies reported iron-60 in meteorites at levels that seemed to confirm a supernova origin. But later, more careful measurements, accounting for contamination and using improved mass spectrometry, found the initial iron-60 abundance in the early solar system to be considerably lower than first reported, and lower than what a nearby supernova would be expected to deliver. Some researchers now argue the low iron-60 levels are more consistent with the aluminum-26 having come from the wind of a massive Wolf-Rayet star, or from a somewhat more distant and diluted supernova contribution mixed in from the broader galactic background, rather than one specific catastrophic explosion right next door. This matters because it means the supernova trigger story, while still a live mainstream candidate, is genuinely contested in the current research literature, not a settled fact being simplified for television. Different meteorite samples, different labs, and different modeling assumptions have produced different iron-60 numbers, and reconciling them is an active area of cosmic chemistry research as of the most recent published work. Some scientists favor a supernova at a specific, calculable distance, often estimated at somewhere between half a light year and a few light years, close enough to deliver isotopes efficiently, but far enough that the young solar system wasn't sterilized by radiation. Others favor scenarios involving multiple massive stars contributing isotopes gradually over the cloud's lifetime, more like background seasoning than a single dramatic event. Others still argue the aluminum-26 abundance we see is actually typical of star-forming regions in general, meaning our solar system's birth cloud may not have needed anything unusual happening nearby at all. It may simply have been born, like most stars, inside a cluster already laced with recycled isotopes from the massive stars that inevitably form and die quickly in any large stellar nursery. What we can say with real confidence: the early solar system's solids do carry the chemical fingerprints of nearby, recent, massive star nucleosynthesis. What remains debated is whether that fingerprint came from one specific nearby supernova that also triggered collapse, from stellar winds without an explosion, or from the general isotopic background of a star-forming region the Sun happened to be born inside, a region that, statistically, almost certainly did contain massive stars living fast and dying young nearby, whether or not one specific explosion get the credit for pushing our particular cloud fragment over the edge. It's also worth noting what this evidence does not tell us. It doesn't tell us anything about a single trigger moment, the way a doomsday date on a birth certificate would. Cloud collapse in real star-forming regions is typically a somewhat gradual, turbulence-driven process happening across many overlapping fragments simultaneously, and a nearby supernova's shockwave, if it happened, would have been one contributing factor among several rather than a single decisive switch flipped on an otherwise static cloud. Aluminum-26 and iron-60 aren't the only short-lived radioactive isotopes cosmochemists have found traces of in these ancient meteorite inclusions, and the fuller isotopic inventory adds real texture to the picture rather than just repeating the same argument twice. Manganese-53, decaying into chromium-53 with a half-life of about 3.7 million years, shows up in primitive meteorites at abundances broadly consistent with production in the same recent burst of nearby massive star nucleosynthesis, invoked for aluminum-26, though its longer half-life makes it a somewhat blunter chronological tool. Iodine, decaying into xenon-129 with a half-life of about 15.7 million years, and plutonium-244, with a half-life of about 80 million years, are longer-lived still. And because they survive longer, they're less useful for pinning down the exact moment of a nearby stellar trigger, but more useful for dating processes that happened over the tens of millions of years after the solar system's solids first condensed. Things like when individual asteroids sealed themselves off from further gas loss, information cosmochemists extract using what's called the iodine-xenon dating system. Taken together, this wider suite of now extinct radionuclides paints a picture of a birth cloud that wasn't simply seeded once and left alone, but one embedded, for some span of time, in a chemically active neighborhood, plausibly a crowded stellar nursery where massive stars were forming, living fast, and dying on timescales of only a few million years. Exactly the kind of environment where a new supply of freshly synthesized isotopes could keep arriving in pulses rather than a single clean injection. It's worth pausing to note that the basic shape of this story, a rotating cloud collapsing into a disk that then built the sun and planets, is not a recent invention dressed up with modern isotope data. The German philosopher Immanuel Kant proposed a version of it in 1755, followed independently by the French mathematician Pierre-Simon Laplace in 1796, both arguing, using nothing more than Newtonian mechanics and careful reasoning, that a flattened, rotating nebula was the natural precursor to a star and its planets. For roughly a century and a half afterward, the nebular hypothesis competed with rival ideas, including an early 20th century proposal by Thomas Chamberlain and Forrest Moulton, suggesting the planets condensed from material torn out of the sun by a close stellar encounter. A model eventually abandoned once physicists showed that material pulled from the sun that way would simply be too hot to condense into planets rather than cool into them. The nebular hypothesis was rehabilitated and put on firmer physical footing in the mid-20th century, notably through the work of Soviet astronomer Viktor Safarnov, whose 1969 book laid out much of the mathematical framework for planetesimal accretion still used, in updated form, by researchers today. Safarnov's equations for estimating planetary growth timescales remain influential enough that a key parameter in accretion theory, the Safarnov number, still carries his name. What's changed since Kant and Laplace's era isn't the basic architecture of the idea: cloud collapses, spins up, flattens, builds a star and a disk, but the sheer density of direct physical evidence now available to test it. Isotope measurements precise to parts per million, spacecraft that have flown through and sampled real disk-forming material, and radio telescopes capable of photographing the process happening around other stars in real time. It's a rare case in the history of science where an idea born entirely from theoretical reasoning, centuries before the technology existed to check it, has held up this well against the flood of evidence that eventually arrived. With all of that on the table, we can move to what happened once collapse, however it started, actually got underway, because this next part is on considerably firmer observational footing. 1710, Chapter 2, A Cloud Becomes a Disk, Angular Momentum and the Architecture of Chaos. Once gravity wins locally, collapse is fast on cosmic timescales, something like a few 100,000 years to go from a diffuse, light-year-scale fragment to a dense, compact, spinning core only a tiny fraction of that size. To understand why the end result was a disk, and not just a growing ball of gas, you need to understand angular momentum, and it's worth taking this slowly, because it is genuinely the single physical principle that determined the entire architecture of everything that followed. Every planet's orbit, every moon, the very shape of the solar system as a flattened plane rather than a sphere. Every molecular cloud has at least some rotation, even if it's imperceptibly slow, a residual spin left over from the cloud's turbulent motion within the larger galaxy, the same way water in a bathtub, even if you didn't deliberately swirl it, tends to have some faint net rotation before it drains. Angular momentum is a conserved quantity in physics. Absent some external force acting on a system, its total angular momentum stays constant. That means as the cloud fragment's radius shrank, collapsing from something like a light year across down to a region only a few times the size of the current solar system, its rotation had to speed up dramatically to conserve that quantity, for exactly the same reason a figure skater spins faster when she pulls her arms in toward her body. A slowly turning cloud a light year across became a rapidly spinning, flattening structure, for the same reason pizza dough spreads into a flat disk when you spin it. Material can collapse efficiently along the rotation axis, where nothing opposes it, but material trying to collapse perpendicular to that axis in the plane of rotation gets held up by its own centrifugal motion. The compromise the physics settles on is a disk, collapsed thin in one direction, spread wide in the other. This is not a minor detail dressed up as a big reveal. It's the reason the solar system is flat. Every planet orbiting close to the same plane, every moon of Jupiter and Saturn lined up in roughly that same plane, the asteroid belt, most of the Kuiper belt, all of it inherited its geometry from the leftover spin of a cloud fragment that, if the physics had shaken out even slightly differently, might have collapsed with less net rotation and produced something rounder, or with more, and produced something more extended and slower to condense. The flatness of the solar system isn't decoration. It's a fossil record of angular momentum conservation, acting on a specific, measurable, physically inevitable process. Material kept falling inward from all directions as the core continued to grow. But because of that spin, infalling gas couldn't simply collapse into a point. It landed instead onto the outer edges of the growing disk, spiraling gradually inward through the disk material already there, transporting angular momentum outward as it went. A process astronomers describe using something called viscous evolution, where friction and turbulence within the disk itself allow material to slowly migrate toward the center, while a smaller fraction of material and angular momentum gets pushed outward, spreading the disk's outer edge even wider over time. This is where the chaos in this story's title stops being a figure of speech. At this stage, the disk was turbulent, threaded with magnetic fields that coupled to the ionized portions of the gas and helped drive material inward through a mechanism called magnetorotational instability, riddled with shockwaves, spiral density waves, and localized clumps of higher and lower density. Not the placid, smooth ring you might picture from a textbook diagram, but a genuinely violent, roiling, three-dimensional environment with temperature differences of hundreds of degrees between its warm inner edge and its frigid outer reaches, and pressure and density gradients steep enough to sculpt the very structures that would eventually seed planet formation. We know none of this is speculation dressed up as fact, because we can watch it happening elsewhere in the galaxy right now, in real time, with modern instruments. The Atacama Large Millimeter/Submillimeter Array, ALMA, a network of radio dishes spread across the high desert plateau of northern Chile, has imaged dozens of these protoplanetary disks around young stars in nearby star-forming regions, and the images are not abstractions. The 2014 ALMA image of the disk around HL Tauri, a star roughly 450 light-years away and only about 1 million years old, showed a system of sharply defined concentric bright and dark rings that stunned even the astronomers who took the picture, because textbook models at the time hadn't predicted disks would show such crisp structure at such a young age. Those gaps are widely interpreted as the gravitational fingerprints of forming planets already clearing lanes in the surrounding material, though the community continues to debate exactly how many of the observed gaps in disks like HL Taus are caused by actual embedded planets versus other processes, like snow lines or disk instabilities, that can also produce ring-like structure without a planet present. Other systems have added to the picture. The disk around the young star PDS-70 gave astronomers something even more direct. 2 actual, confirmed planets, PDS-70b and PDS-70c, caught mid-formation, imaged directly within a gap in their parent disk, accreting gas in real time, about as close to a photograph of our own solar system's Jupiter, and Saturn being born as science has ever produced. Disks like TW Hydra and systems showing dramatic spiral arm structures like Ilia's 227 have added further evidence that gravitational instabilities and embedded planets sculpt these disks in ways that vary considerably from system to system. None of this is a reconstruction from indirect clues alone. It's direct imaging of the same basic process our own solar system went through 4.5 billion years ago, happening in other corners of the Milky Way today. The disk's vertical structure mattered just as much as its radial structure for how planet formation eventually proceeded, and it's worth explaining briefly here since it connects the disk physics of this chapter directly to the dusk growth story ahead. A protoplanetary disk isn't a uniform slab. It's hottest and most turbulent near its surface layers, where stellar and interstellar radiation penetrates most easily, and progressively cooler, denser, and calmer toward its geometric midplane, shielded by the overlying gas and dust from much of that radiation. Dust grains, being far more massive relative to their surface area than individual gas molecules, feel the disk's turbulence less and gravity's pull toward the midplane more, and over time they settle vertically, concentrating into an increasingly thin, dense layer sandwiched within the surrounding gas, a process astronomers can now directly observe in real disks. Since ALMA and infrared imaging of systems like HD 163,296 have captured resolved, vertically thin dust layers sitting within a visibly thicker, surrounding gas disk. This settling is not a footnote. It's a precondition for everything covered in a later chapter of this documentary, because concentrating dust into a thinner, denser midplane layer is exactly what raises the local ratio of solids to gas high enough for processes like the streaming instability to actually operate. And calculations suggest that without at least some degree of vertical settling, the solid-to-gas ratios needed to trigger runaway pebble concentration would likely never be reached at all. Turbulence works against this settling, stirring dust back upward and preventing it from fully concentrating, which means the balance between a disk's turbulence and its dust settling rate is itself one of the more delicate, actively studied variables governing weather, and how quickly a given region of a given disk successfully makes the leap from scattered dust to bound planetesimals. Compounding the challenge, settled dust doesn't just sit still radially either. Smaller grains and pebbles, still coupled to the gas through drag, tend to drift slowly inward through the disk over time even after settling vertically, a process called radial drift that can, in some models, remove solid material from a given region faster than local growth can consume it, adding yet another timing pressure to the already narrow window planetesimal formation has to work within. The mechanism actually responsible for moving material inward through the disk and transporting angular momentum outward, described a moment ago in general terms as viscous evolution, has itself been the subject of a significant and fairly recent shift in scientific thinking, and it's worth walking through because it's a good example of a model evolving in response to better physics rather than better observations alone. For decades, the standard approach, developed by Nikolai Shakura and Rashid Sunyaev in the early 1970s, treated disk turbulence as a kind of effective friction, parameterized by a single dimensionless number called alpha, without needing to specify exactly what physical process generated that turbulence in the first place. Magnetorotational instability, mentioned earlier as one of the disk's genuinely chaotic features, was for a long time the leading candidate to explain where that turbulence and the resulting alpha viscosity actually came from ionized gas coupling to a weak magnetic field threading the disk, generating turbulent stresses that drove material inward. More recent theoretical and computational work, however, has complicated that picture considerably. Detailed non-ideal magnetohydrodynamic simulations, incorporating effects like ambipolar diffusion and the Hall effect that become important in the cold, weakly ionized conditions typical of a real protoplanetary disk's interior, suggest that magnetorotational instability may actually be suppressed across large regions of the disk, sometimes called dead zones, where ionization is too low to sustain it. If large stretches of the disk really are magnetically dead in this sense, something else has to be doing the work of driving accretion, and the leading alternative candidate to emerge over roughly the past decade is a large-scale magnetized disk wind, material launched vertically off the disk's surface along magnetic field lines, carrying angular momentum away with it as it escapes, rather than transporting that angular momentum outward through in-plane turbulence alone. This is not a settled question. Different disk models, applied to different regions and different stages of disk evolution, currently favor different combinations of magnetorotational turbulence, dead zones, and wind-driven accretion, and reconciling these mechanisms with the growing catalog of ALMA observations remains an active frontier of disk physics research as of the most recent published work. ALMA's disk images have also exposed a genuine puzzle that researchers refer to, somewhat bluntly, as the missing mass problem. When astronomers estimate the total mass of solid material in an observed protoplanetary disk, they typically do it indirectly, measuring the faint millimeter wavelength glow emitted by dust grains, and then converting that brightness into an estimated dust mass using assumptions about grain composition and how efficiently dust of a given size radiates at that wavelength. When those estimates are added up across large samples of disks in nearby star-forming regions, a striking pattern emerges. Many observed disks appear to contain only a fraction of the solid material that would be needed to build the population of planets, including giant planets and the growing catalog of exoplanets with substantial rocky or icy cores that surveys suggest typically forms around stars like these. Several explanations have been proposed, none yet decisively confirmed. One possibility is that planet formation happens fast, and by the time a disk is a few million years old and observable in a typical ALMA survey, much of its original solid mass has already been locked up into larger, centimeter to kilometer scale bodies that simply don't radiate efficiently at millimeter wavelengths, and therefore go undetected by the very technique used to estimate disk mass in the first place, meaning the missing mass isn't missing at all, just already converted into planetesimals hiding in plain sight. Another possibility is that standard assumptions about dust grain properties, particularly how porous or fluffy young dust aggregates are systematically underestimating how much mass a given amount of millimeter emission actually represents. A third possibility is that some disks are simply optically thick in their innermost, densest regions, hiding additional mass from view entirely. Resolving this puzzle matters well beyond academic tidiness, because it bears directly on how confident astronomers can be that the disk-to-planet formation pathway described throughout this chapter, and inferred for our own solar system's history, is actually efficient enough, and starts with enough raw material, to explain how common planetary systems turn out to be across the galaxy. 2945, Chapter 3, A Star Lights Up, From Protostar to TTAURI to Solar Wind. At the center of the collapsing, flattening structure, where the overwhelming majority of the system's mass had accumulated, pressure and temperature kept climbing as gravitational energy converted into heat. This central object went through recognizable, well-studied evolutionary stages on its way to becoming a star, and astronomers classify young stellar objects elsewhere in the galaxy using exactly this sequence, because we've observed enough of them at each stage to be confident in the general pattern. In the earliest phase, the protostar is deeply embedded, wrapped in so much surrounding gas and dust that it's essentially invisible in ordinary light, detectable mainly through the infrared glow of the material around it, and through jets of material launched outward along its rotation axis. A phenomenon called bipolar outflow, observed in countless young stellar systems, where some of the infalling material is redirected by magnetic fields and launched away from the star at speeds of hundreds of kilometers per second, carrying away excess angular momentum that would otherwise choke the star's ability to keep growing. As the surrounding envelope of gas thins out through continued infall and these outflows, the young star becomes progressively more visible, moving through what's called the T-Tauri phase, named for the prototype star T-Tauri in the constellation Taurus, discovered to have unusual, variable brightness in the 19th century, and later understood to represent an entire class of young, still-forming stars. Classical T-Tauri stars are characterized by strong, variable stellar winds, intense X-ray and ultraviolet flaring far exceeding anything the mature Sun produces today, and continued accretion of gas directly from their surrounding disk onto the stellar surface, which shows up as excess ultraviolet emission and distinctive spectral signatures that astronomers use to measure accretion rates in these systems directly. This phase can last anywhere from roughly 1 million to 10 million years, depending on the star's mass and the properties of its surrounding disk. And it is during this phase that the growing central object finally crosses the threshold that makes it a true star rather than merely a very hot ball of collapsing gas. That threshold is hydrogen fusion. Eventually, the core got hot and dense enough, somewhere in the range of 10 million Kelvin at its center, with core pressures crushing hydrogen nuclei together hard enough and often enough to overcome their mutual electrical repulsion, for hydrogen to begin fusing into helium through the proton-proton chain reaction, releasing the energy that would define this star's output for the next 10 billion years. That ignition marked the birth of the Sun as we'd recognize it, and it's worth sitting with how completely it changed the rules of everything around it. Before ignition, the young Sun was still growing, still pulling in material, still fundamentally just the largest lump of matter in a disk full of smaller lumps. After ignition, it was radiating enormous, sustained energy outward, heating the inner disk, driving off lighter volatile gases from the regions closest to it, and setting in motion the process that would eventually clear the nebula away entirely. That clearing process deserves its own attention, because it's one of the more dramatic and comparatively well-understood chapters of the disk's life. As the young Sun's T-Tauri wind and radiation intensified, and as its X-ray and ultraviolet output heated the upper layers of the surrounding gas disk, a process called photoevaporation took hold. Gas at the disk's surface, heated enough to exceed the local escape velocity, simply flowed away into space, gradually and then rapidly thinning the disk from the inside out and from the top down. Observations of other young star systems have caught disks in exactly this act of dispersal, some showing an inner hole opening up first, consistent with a young star's radiation carving out the closest material while an outer disk lingers longer, a pattern strong enough that astronomers can estimate typical disk lifetimes across many systems. Most protoplanetary disks appear to disperse within about 5 to 10 million years of their star's formation, which places a hard ceiling on how long any gas-dependent planet-forming process, like giant planet gas accretion, actually has to work with before its raw material disappears for good. External photoevaporation adds a second layer to this story for stars, like the Sun, that may have formed within a larger cluster containing massive, hot, radiation-heavy stars nearby. The Orion Nebula, a relatively nearby and intensively studied star-forming region, contains striking examples called proplyds, externally illuminated protoplanetary disks, imaged directly by the Hubble Space Telescope, whose outer material is visibly being stripped away by the intense ultraviolet radiation of nearby massive stars, forming glowing, comet-like tails of escaping gas pointed away from the radiation source. If the Sun's birth cluster contained similarly massive, radiation-heavy neighbors, plausible, though not something we can verify directly for our own specific birth cloud. The young solar disk may have experienced both its own star's internal photoevaporation and this kind of external stripping simultaneously, compressing the available window for planet formation even further. And notice the scale that resulted from all of this. The planets, every single one of them combined, formed from roughly 0.1% of the material that existed in the original disk. The Sun is not one player among 9 or 10. The Sun accounts for something on the order of 99.8% of the mass of the entire solar system. The Sun is the story, and the planets are the crumbs left on the table after it finished eating. And it's worth remembering that the very same violent processes that let the Sun claim nearly everything are the processes that also determined how much raw material was left over, and for how long, for the planets still forming around it to work with. The 5 to 10 million year disk lifetime estimate mentioned earlier isn't derived from any single system's history. It comes from a technique astronomers call discfraction surveys, and it's worth explaining because it's one of the more elegant pieces of supporting evidence in this whole chapter. Rather than watching one disk disperse over time, which would take longer than most research careers, astronomers instead observe many different star clusters of different known ages and simply count what fraction of young stars in each cluster still show infrared or millimeter evidence of a surrounding disk. Extremely young clusters, only a million years old or so, show disk fractions approaching 80 or 90%. Nearly every young star still has one. Clusters a few million years old show that fraction dropping steadily. By around 10 million years, in most surveyed clusters, the disk fraction has fallen to only a few percent, and by 20 million years, disks are essentially gone entirely. Pioneering work along these lines by researchers including Charles Latta and Carl Heisch in the early 2000s, using infrared data from ground and space-based telescopes across numerous nearby star-forming regions, established this declining disk fraction pattern clearly enough that it's now treated as one of the more reliable, independently reproduced timelines in the entire field. A genuine statistical measurement built from thousands of individual young stars, rather than an assumption built into the models used to interpret them. This same body of survey work also bears on a question about the Sun's own birth environment that's easy to overlook. How many other stars was the Sun actually born alongside? Stars form in clusters ranging enormously in size, from small groups of only a few dozen members to massive clusters containing tens of thousands of stars. And the size of that birth cluster matters directly for the isotope story covered earlier in this documentary, because only a sufficiently large cluster is statistically likely to contain the massive, short-lived stars capable of producing meaningful quantities of aluminum-26 and iron-60 within the tight timeframe the meteorite evidence demands. Dynamical arguments, based on things like the current spacing and orbital properties of the outer solar system's more distant small bodies, which would likely have been disturbed differently by close stellar encounters in a denser versus sparser birth cluster, combined with the isotope evidence itself, have led researchers including Fred Adams, in an influential 2010 review, to argue the Sun most likely formed in a cluster containing somewhere between a few hundred and a few thousand stars, dispersing within a few tens of millions of years as the cluster's own gravity gradually lost its grip, and its member stars drifted apart into the wider galaxy, the Sun among them. That dispersal, incidentally, explains why the Sun today has no identifiable stellar siblings. Whatever cluster it was born inside scattered so long ago, and has mixed so thoroughly into the general galactic population over 4.5 billion years of orbital motion, that picking out the Sun's original birthmates from among the roughly 100 billion other stars in the Milky Way has so far proven beyond even modern astrometric surveys. Though researchers using extremely precise stellar motion data from missions like Gaia continue to search for candidate siblings by tracing stellar orbits backward in time. 4110, Chapter 4, Dust Learns to Clump, the meter-size barrier and how nature probably cheated it. With the Sun burning at the center and its wind and radiation beginning the slow work of clearing the nebula, the surrounding disk of gas and dust began its long transformation into solid worlds. It started small and unglamorous. Microscopic dust grains, silicate minerals, metallic iron, carbon compounds, and beyond the frost line, ices, collided at low relative speeds within the turbulent gas and stuck together through simple electrostatic attraction, and in some cases, direct chemical bonding, not so different from dust bunnies accumulating in the corner of a room, just happening across an entire solar system's worth of material instead of a floor. Laboratory experiments, including drop tower and parabolic flight experiments designed to simulate the low gravity, low pressure conditions of a protoplanetary disk, have directly confirmed that this kind of low-speed sticking works for grains ranging from microscopic dust up to roughly centimeter-sized clumps, giving this early stage of growth solid experimental grounding rather than pure theory. Grains built into pebbles, and pebbles, in principle, should build into boulders, and boulders into objects a kilometer or more across, called planetesimals. But here's where the story runs into a genuine, well-documented, and, despite decades of research, still not fully resolved problem, sometimes called the meter-size barrier, and it's worth explaining carefully because it isn't a minor technical footnote. It's one of the central open questions in all of planet formation theory. Once dust and pebbles grow past roughly centimeter scale, laboratory and computational studies both show that further growth through simple sticking collisions becomes far less reliable. Objects in this intermediate size range tend to bounce off each other rather than stick, in what's called the bouncing barrier, or in higher speed collisions, they shatter rather than merge, in what's called the fragmentation barrier. Worse, objects around a meter in size face an entirely separate problem that has nothing to do with collisions at all: aerodynamic drag from the surrounding gas. The gas in a protoplanetary disk is partially supported against the sun's gravity by its own pressure, which means it orbits slightly slower than a solid object at the same distance would if gravity alone were acting on it. A meter-sized object, orbiting at the faster, purely gravitational speed, constantly plows into a headwind of slower-moving gas, and that headwind robs it of orbital energy. Calculations show that at roughly meter scale, this drag is strong enough to make an object spiral into the sun in as little as a few hundred to 1,000 orbits, which, in the inner solar system, could mean losing the object to the sun in as little as a few hundred years. That is a dramatically short window on the timescale of millions of years the disk otherwise has available, and it creates a genuine bottleneck. Objects need to somehow leap past this size range quickly, or they simply don't survive to grow further. For a long time this was treated as a serious unsolved problem, and to a real extent it still is. There is no single, universally agreed mechanism, confirmed by direct observation, that fully explains how the disk reliably crossed this gap. But the theoretical and computational work of the past 2 decades has produced genuinely promising candidates, and among planetary scientists, confidence has grown considerably that we at least understand the right general category of solution, even without full consensus on the precise details. The leading candidate is called the streaming instability, first modeled in detail by astronomers Andrew Youden and Jeremy Goodman in the mid-2000s, and refined extensively since through increasingly sophisticated computer simulations, notably by Anders Johansson and collaborators. The core idea is that pebbles aren't just passive passengers being pushed around by gas. They also exert a small aerodynamic feedback on the gas itself. In regions where pebbles happen to be slightly more concentrated than average, that feedback locally reduces the headwind the pebbles experience, which lets them drift inward more slowly than surrounding pebbles, which causes even more pebbles to pile up in that same region, in a runaway, self-reinforcing feedback loop. Given enough time and the right local conditions, particularly a moderately elevated ratio of solid pebbles to gas, simulations show this process can concentrate pebbles into dense clumps that become gravitationally bound and collapse directly into planetesimals tens to hundreds of kilometers across, skipping the fragile, dangerous meter-sized stage almost entirely rather than grinding through it collision by collision. A closely related and complementary idea is pebble accretion, developed extensively by Michiel Lambrechts and Anders Johansson, which describes how, Once a modest number of planetesimals do form through something like the streaming instability, they can then grow further not primarily by colliding with similarly sized bodies, but by gravitationally gathering the huge, steady reservoir of smaller pebbles still drifting slowly through the disk under gas drag. Because these pebbles are experiencing drag rather than moving purely ballistically, a growing planetesimal's gravity can capture them far more efficiently than classical models of solid-body collision would predict, dramatically speeding up growth, particularly for the cores of the giant planets, which needed to reach substantial size while gas was still available in the disk to be captured. We have physical evidence beyond simulations that something like this actually happened, and it comes from an unexpected source. A small, reddish, contact binary object roughly 1 billion miles beyond Pluto's orbit called Arrokoth, visited by NASA's New Horizons spacecraft on a close flyby on New Year's Day of 2019, several years after that same spacecraft's historic encounter with Pluto. Arrokoth turned out to be two lobes gently stuck together, with a shape, rotation, and surface geometry that strongly suggests they merged at extremely low relative velocity, rather than the higher speed, more violent collisional accretion older models predicted for planetesimal formation. That gentle merger is broadly consistent with what streaming instability-driven planetesimal formation predicts. Bodies forming directly at tens of kilometers scale, from a local collapse of concentrated material, rather than a long, violent collisional ladder climbing up from small fragments. Arrokoth is thought to be a relatively pristine, largely unaltered relic of the solar system's original cold classical Kuiper belt population, meaning its structure may preserve information about planetesimal formation itself, 4.5 billion years later. None of this means the meter-size barrier problem is fully closed. Exactly how universal the streaming instability is across different regions of a disk, exactly what conditions are required to trigger it reliably, and how much it needs to be supplemented by other proposed mechanisms, like localized pressure bumps in the disk that trap pebbles, often associated with the same kinds of rings ALMA has photographed in real disks, remain active topics of ongoing research and genuine scientific disagreement. What is not in doubt, because meteorites and asteroids are the leftover physical proof sitting in collections around the world, is that planetesimals did form in large numbers across the young disk. The end result is certain. The precise mechanism that reliably produced it remains one of the most actively studied open questions in the entire field. Once objects did reach planetesimal size, however they got there, subsequent growth became far more straightforward and far better understood, entering a phase called runaway growth. Bigger bodies have proportionally more gravity, so they sweep up more surrounding material, so they grow bigger faster than their smaller neighbors, in a self-reinforcing process that computer simulations model with a high degree of confidence. Runaway growth eventually transitions into what's called oligarchic growth, where a smaller number of increasingly dominant bodies, protoplanets, begin to gravitationally dominate and stir up the orbits of the remaining smaller planetesimals around them, slowing their own growth rate somewhat as they compete with their nearest rivals for the shrinking pool of remaining material. Within a few million years of this process beginning, the inner disk was crowded with dozens of Moon-to-Mars-sized protoplanets, all on crossing, dynamically unstable orbits, all competing for the same limited reservoir of material. This was not a gentle nursery. It was a demolition derby with the winners getting bigger and the losers getting absorbed, ejected, or shattered. And we'll come back to exactly how violent that derby got when we reach the story of the Moon. Direct physical evidence that at least some planetesimals grew large fast, rather than slowly grinding their way up through repeated collisions over tens of millions of years, comes from an unlikely source. The internal structure of the asteroid Vesta, the second most massive object in the asteroid belt, mapped in detail by NASA's Dawn spacecraft during its orbital mission there, between 2011 and 2012. Vesta turns out to be differentiated, meaning it has a distinct iron core, a rocky mantle, and a crust, layered the way a much larger planet is layered, rather than a uniform, undifferentiated mixture of rock and metal throughout. Differentiation like that requires a body to have gotten hot enough early enough to melt and let denser material sink to the center. And for an object Vesta's size, roughly 525 kilometers across, the most plausible heat source is the decay of short-lived radioactive aluminum-26, the same isotope discussed at length earlier in this documentary, which means Vesta had to accrete to something close to its final size, while aluminum-26 was still abundant. Within the first few million years of the solar system's history, since aluminum-26's 717,000-year half-life means it's essentially gone after 10 or so million years. This isn't just an inference from Vesta's shape. A large collection of meteorites believed to have been blasted off Vesta's surface by later impacts, the Howardite-Eucrit-Diogenite group, commonly abbreviated HED meteorites, some of them directly matched to Vesta through reflectance spectroscopy, comparing their mineral signatures to telescopic observations of the asteroid itself, have been dated using the hafnium-tungsten chronometer, a radiometric system that exploits the decay of hafnium-182 into tungsten-182 with a half-life of about 9 million years, and which is particularly useful for timing core formation specifically, because hafnium and tungsten behave very differently during melting. Hafnium stays in the rocky mantle, while tungsten preferentially sinks into the metallic core. Measurements of these meteorites' tungsten isotope ratios point to Vesta's core forming within roughly the first 3 million years after the solar system's oldest solids condensed, a remarkably short window that stands as some of the most direct physical proof available that large planetesimal accretion, at least for some bodies, genuinely could happen fast, lending real, independent support to fast formation mechanisms like the streaming instability discussed earlier. Rather than leaving that idea to rest on computer simulations and Arakoth's gentle merger alone. 5345 Chapter 5 The Frost Line, 1 temperature threshold, 2 entirely different solar systems. Not all of the disk's raw material was available everywhere, and understanding why requires understanding basic condensation chemistry rather than anything exotic. Close to the young, blazing sun, temperatures in the inner disk were far too high for anything except rock-forming minerals and metals, silicates, iron, nickel, and related compounds with high condensation temperatures, to condense out of the gas into solid grains. Water, ammonia, methane, and other volatile compounds simply couldn't freeze into ice under those conditions. They remained vapor, unable to form solid grains that dust could accumulate onto, and largely unable to contribute to solid planet-building material in that hot inner zone. So the planets that assembled there, Mercury, Venus, Earth, and Mars, built themselves almost entirely out of rock and metal, and stayed comparatively small, because rock and metal-forming elements were only ever a modest slice of the disk's total elemental inventory. Hydrogen and helium dwarf everything else in a protoplanetary disk's composition by mass, and the heavier rock-forming elements are a distant minority even among the non-gaseous material. Farther out, past a boundary astronomers call the frost line, or snow line, its exact original location debated but generally estimated to have sat somewhere in the vicinity of where the asteroid belt orbits today, roughly 2.5 to 4 astronomical units from the Sun. Temperatures dropped low enough, likely below about 150 to 170 Kelvin depending on local pressure, for water ice to condense directly out of the disk gas into solid form. Farther out still, additional, more exotic frost lines existed for more volatile compounds like carbon dioxide, carbon monoxide, ammonia, and methane, each freezing out at its own characteristic temperature, and therefore its own characteristic distance from the Sun, creating a layered, onion-like structure of chemical availability across the disk, rather than one single sharp dividing line. That water ice frost line in particular reshaped the entire outer solar system's building project, because ice, once it became available as a solid, was abundant. There was simply far more icy material accessible in the outer disk. Once you added water, ammonia, and methane ice to the rocky and metallic material also available there, than there ever was rocky and metallic material alone in the hot inner disk. Protoplanets forming beyond the frost line had access to a dramatically larger reservoir of solid building material, and could therefore grow rock-and-ice cores considerably faster and considerably larger than anything forming closer to the Sun. This is where the leading theoretical framework for giant planet formation, called core accretion, comes in, developed in detailed quantitative form by researchers including James Pollock and collaborators in the mid-1990s, and refined extensively since. The model proposes that once a growing rock-and-ice core beyond the frost line reached a critical mass, generally estimated at somewhere around 10 times the mass of the Earth, its gravity became strong enough to begin pulling in the surrounding hydrogen and helium gas from the disk directly, rather than merely accreting solid material. Below that critical threshold, gas accretion proceeds slowly and is easily outpaced by the core's own solid growth. Above it, the process can enter a runaway phase, with the growing envelope of gas itself adding enough additional mass and gravity to pull in still more gas, potentially gathering hundreds of Earth masses of hydrogen and helium in a relatively short span of time, so long as the surrounding disk gas hadn't yet been cleared away by the young sun's photoevaporation. That's the proposed origin of Jupiter and Saturn, rock-and-ice cores, built quickly beyond the frost line while raw material was still abundant, that crossed the runaway threshold while the gas disk was still present, and wrapped themselves in atmospheric envelopes thousands of kilometers deep as a result. Uranus and Neptune present a more complicated case for the core accretion model, and this is worth being honest about rather than glossing over. They formed farther out still, in a region of the disk where material was sparser and orbital periods were long enough that simple core accretion, run at face value, would have taken far longer to build a sufficiently large core than the few million-year lifespan of the gas disk actually allowed. A genuine timing problem researchers have spent considerable effort addressing. Proposed solutions include the possibility that Uranus and Neptune's cores actually formed closer to the Sun, in a denser part of the disk where growth could proceed faster, and migrated outward to their current positions afterward. An idea that connects directly to the giant planet migration story we'll cover later in this documentary. Whatever the precise mechanism, the observational result is that Uranus and Neptune ended up with smaller, less massive gas envelopes than Jupiter and Saturn, composed of a larger relative proportion of heavier ices and rock, earning them the separate classification of ice giants, rather than true gas giants, a distinction reflected directly in their bulk density and their considerably higher fraction of heavier elements compared to hydrogen and helium. It's worth flagging that core accretion is not the only theoretical model ever proposed for giant planet formation. An alternative, called the disk instability model, championed prominently by researcher Alan Boss, proposes that under the right conditions, a sufficiently massive, sufficiently cold and unstable region of a protoplanetary disk could collapse directly under its own gravity into a giant planet in a matter of a few hundred to a few thousand years, without needing to first build a solid core at all. Essentially, a scaled-down version of the same gravitational collapse that formed the Sun itself, happening within its own leftover disk. Most researchers today consider core accretion the better supported explanation for giant planets in our own solar system, given how well it explains the correlation between a star's metal content and its likelihood of hosting giant planets, along with the internal structure evidence for substantial cores inside Jupiter and Saturn. returned by NASA's Juno and Cassini missions respectively. But disk instability remains a live candidate specifically for explaining certain wide-orbit giant exoplanets discovered at distances from their host stars, where core accretion's timescale problem becomes severe, and the relative contribution of each mechanism across the full population of known giant planets remains a genuinely active research question rather than a fully closed case. What makes the frost line concept, broadly speaking, one of the best supported ideas in the entire field of planet formation is that it isn't just a story tailored after the fact to explain our own particular solar system's layout. It makes testable predictions, and those predictions have held up well against an enormous new body of evidence. The more than 5,000 confirmed exoplanets now cataloged across other star systems, largely through NASA's Kepler and TESS missions, along with ground-based surveys, show statistical patterns, gas giants showing up disproportionately at larger orbital distances from their host stars relative to smaller rocky worlds, and the overall frequency of giant planets correlating with the heavy element content of the host star, exactly as core accretion theory predicts, that give this general framework considerable independent support, well beyond our single solar system's example. The frost line's influence on solar system chemistry extends into a question that remains genuinely, actively debated. Where did Earth's water actually come from? Earth formed inside the frost line, in the hot, rocky metallic inner disk where water ice couldn't condense directly, which means the water filling Earth's oceans today was almost certainly delivered from farther out, after Earth's initial rocky assembly, rather than accreted locally as ice from the start. The question is which class of outer solar system object did the delivering, and the leading way researchers try to answer it is by comparing the ratio of deuterium to ordinary hydrogen, called the DH ratio, in Earth's ocean water against the same ratio measured in candidate source populations, since that ratio varies measurably depending on where and how a body's ice originally formed, and has proven to be a reasonably durable chemical fingerprint over billions of years. For a long time, comets were the intuitive favorite, given their obvious ice content and their well-known habit of striking planets throughout solar system history. But measurements of several comets' DH ratios, including a particularly precise result returned by the European Space Agency's Rosetta mission, which orbited and closely studied Comet 67P/Churyumov-Gerasimenko between 2014 and 2016, found a DH ratio roughly 3 times higher than Earth's ocean water, a mismatch serious enough to rule out Jupiter family and Oort cloud-type comets, at least the specific ones measured so far, as the dominant source of Earth's water, even though a handful of other comets measured before Rosetta had shown ratios closer to Earth's, muddying any simple story. Carbonaceous chondrite meteorites, primitive, water and organic-rich rocky material, generally believed to originate from the outer asteroid belt, beyond the frost line but considerably closer to the Sun than any comet's typical home, tend to show DH ratios that match Earth's ocean water considerably more closely and consistently than the comet measurements do. That comparison has shifted most researchers' favored explanation toward asteroids, rather than comets, as the dominant water source, with delivery plausibly happening either through direct accretion of water-bearing material during Earth's original formation, or through a later bombardment of water-rich asteroids scattered inward from the outer belt, potentially including delivery during the same broad bombardment era discussed later in this documentary. The debate isn't fully closed. The observed comet sample remains small. Cometary DH ratios show more diversity than early theory expected, and some researchers continue to argue for a mixed source origin, combining both asteroidal and cometary contributions in proportions that are still being actively worked out. But it stands as a clear, concrete example of how a single measurable chemical ratio, applied carefully across different classes of solar system bodies, can meaningfully constrain a question as basic and as consequential as where the water in your own body ultimately came from. 10510 Chapter 6 Building Rocky WRLDS Chaos, Collisions, and the Grand Tack Question. While the outer disk was busy building gas and ice giants beyond the frost line, the inner disk was running its own, very different building project. And it's worth spending real time here before we get to the specific, singular collision that built our moon, because the terrestrial planets as a group emerged from a broader, longer, genuinely chaotic process that deserves to be understood on its own terms. By perhaps 10 to 100 million years after the Sun ignited, a wide range that reflects real uncertainty in how long the final stages actually took, since these growth timescales depend sensitively on assumptions that vary between models. The inner solar system's population of dozens of Moon-to-Mars-sized protoplanets had been gradually winnowed down through repeated collisions toward a smaller number of larger survivors. Early, still-forming versions of Mercury, Venus, Earth, and Mars. Computer simulations of this process, called n-body simulations, because they track the gravitational interactions of many individual bodies simultaneously, consistently show that this final assembly stage was chaotic in the precise mathematical sense of the word. Small differences in starting conditions produce wildly different final outcomes, meaning that no simulation, however sophisticated, currently predicts the exact final arrangement of terrestrial planets with certainty. Instead, researchers run large numbers of these simulations and look for patterns that show up reliably across many different random starting conditions, treating those recurring patterns as more likely to reflect real physical tendencies rather than accidents of one particular simulation run. One recurring pattern that troubled researchers for years is that standard n-body simulations of terrestrial planet formation, run without any special adjustments, tend to overproduce Mars's mass by a significant margin, often building a fourth terrestrial planet several times more massive than the real Mars actually is, while also tending to produce an asteroid belt with a different compositional mixture than the one we actually observe, which contains an unusual, seemingly out-of-place blend of both dry, rocky asteroids and water-rich, more primitive carbonaceous asteroids sitting side by side in overlapping orbital regions. This is where a proposed model called the Grand Tack, developed by researchers Kevin Walsh, Alessandro Morbidelli, Sean Raymond, David O'Brien, and Avi Mandel in a widely discussed 2011 paper, enters the story. And it's important to be clear from the outset that this is a considerably more debated, less universally accepted model than most of what we've covered so far in this documentary, offered here specifically because it addresses real, documented problems with simpler models, not because it has achieved consensus status. The Grand Tack proposes that Jupiter, while the gas disk was still present, and while Jupiter was still young, migrated inward substantially from its formation location, possibly down to somewhere around 1.5 astronomical units from the Sun, inside the current orbit of Mars, before Saturn, forming and growing behind it, caught up and locked into an orbital resonance with Jupiter that reversed the direction of migration, sending both giant planets migrating back outward again. Like a sailboat tacking against the wind and reversing course, hence the model's name. According to simulations built around this scenario, Jupiter's inward and then outward passage through the inner disk would have gravitationally scattered and truncated the material available for terrestrial planet formation in the Mars-forming region specifically, starving that region of building material and naturally producing a smaller Mars, while simultaneously scattering a mixture of both dry, rocky material from close to the Sun and icy, primitive material from farther out into the asteroid belt region, potentially explaining the mixed compositional population observed there today. The Grand Tack is genuinely elegant, and it has attracted considerable attention and follow-up research precisely because it manages to address two previously separate, stubborn problems: Mars's small size and the asteroid belt's compositional mixing, with a single proposed mechanism. but it remains a debated model rather than an established fact. Critics have pointed out that it depends on specific assumptions about disk properties and migration rates that are difficult to independently verify, that alternative explanations for Mars's small mass exist, including models where the initial disk of solid material was simply thinner in the Mars-forming region from the start, without requiring any giant planet migration at all, and that reproducing the precise, detailed orbital and compositional properties of the terrestrial planets and asteroid belt simultaneously has proven difficult for any single model, Grand TAC included, to achieve consistently across repeated simulation runs. Different research groups continue to publish competing terrestrial planet formation models today, some incorporating a Grand TAC-style migration, some not. And the question of exactly how Jupiter's early history shaped the inner solar system's final architecture remains one of the more actively contested areas of current planet formation research. What's on far firmer ground is the broader claim that terrestrial planet formation was a fundamentally violent, collision-driven process, regardless of exactly how Jupiter behaved during it. The final handful of terrestrial protoplanets that emerged from this process did so through repeated, sometimes enormous impacts between Moon-to-Mars-sized bodies, and Earth's own final assembly included at least one collision so large and so consequential that it deserves its own dedicated chapter, because it didn't just help build Earth. It built something else entirely, still hanging visibly in the sky every night, that changed the future of this planet in ways scientists are still working out the details of today. Before turning to Earth's own defining collision, it's worth pausing on a smaller, stranger anomaly from this same violent era of terrestrial planet assembly: Mercury's bizarrely oversized iron core. Mercury is the smallest planet in the solar system, but proportionally it has by far the largest core relative to its total size. An iron core estimated to make up somewhere around 85% of the planet's radius, wrapped in a comparatively thin rocky mantle and crust, a ratio dramatically higher than Earth's, Venus's, or Mars's. Simple condensation chemistry, of the kind discussed earlier in this chapter regarding the frost line, doesn't naturally explain a discrepancy that large, since Mercury formed close enough to the Sun that its raw material should have been broadly similar in composition to the material that built Venus and Earth, just hotter and slightly more metal-rich at the margins. The traditional explanation, proposed as early as the 1980s, was that Mercury originally accreted with a much more ordinary rock-to-metal ratio, and then suffered one or more giant impacts of its own that blasted away a large fraction of its rocky mantle, leaving the dense metallic core behind as a proportionally larger share of what remained. Broadly the same violent, collisional logic used to explain the Moon, just applied to a different planet with a very different outcome. Detailed computer modeling of this scenario, however, has run into a persistent problem. Producing Mercury's specific, extreme core-to-mantle ratio through a single giant impact generally also strips away far more of the planet's more volatile elements than spacecraft data actually show. It retains measurements from NASA's Messenger mission, which orbited Mercury between 2011 and 2015, found surface abundances of volatile elements like potassium and sulfur that are considerably higher than a mantle-stripping giant impact violent enough to explain the oversized core would be expected to leave behind, creating a genuine tension between the two lines of evidence. An alternative proposed more recently, developed particularly by researchers Eric Asfog and Andreas Rufer, suggests Mercury may instead be the surviving remnant of a hit-and-run collision, a specific category of impact, identified through detailed simulation work on terrestrial planet formation more broadly, in which two roughly similar-sized protoplanets collide at a glancing angle and high enough relative speed that they don't merge at all, but instead partially exchange and strip material before separating again as two distinct, altered bodies, rather than combining the way the Earth-Theia collision is believed to have done. In this scenario, Mercury could represent the stripped, mantle-depleted survivor of such an encounter, having lost a disproportionate share of its outer rocky material to the other, larger body involved, without needing the single catastrophic impact scenario that seems to overpredict volatile element loss. Neither explanation for Mercury's core has achieved the kind of broad consensus the giant impact story enjoys for the Moon, and the question remains a genuinely open one in current research. A reminder that Mercury, close and comparatively small as it is, still hides one of the more stubborn unresolved puzzles from the solar system's earliest, most collision-prone era. 1:1530 Chapter 7, The Moon, a giant impact and the isotope crisis it created. Somewhere in that same window, perhaps 30 to 100 million years after the Sun ignited, the inner solar system had mostly, though not entirely, settled into a handful of dominant protoplanets, early versions of Mercury, Venus, Earth, and Mars. But settled is relative. Collisions were still happening, and one of them changed everything for the world you're standing on right now. The leading explanation for the Moon's existence is the giant impact hypothesis, first proposed in something close to its modern form by researchers including William Hartmann and Donald Davis, and independently by Alastair Cameron and William Ward, in papers published in the mid-1970s, and refined extensively through computer simulation ever since. The core proposal: a Mars-sized protoplanet, commonly given the name Theia after the mythological mother of the moon goddess Selene in Greek mythology, struck the young, still substantially molten Earth in a glancing but colossal collision, releasing energy on a scale almost impossible to fully convey. Models suggest the impact briefly vaporized and partially remelted large portions of Earth's outer layers, while blasting an immense volume of debris, drawn largely from Theia's mantle and Earth's outer layers, into orbit around the newly reshaped planet. That debris disk, according to simulations, coalesced remarkably quickly by geological standards, potentially within centuries to a few thousand years, into the Moon. This isn't a fringe idea being given undeserved airtime. It's the genuine mainstream scientific consensus for how the Moon formed, and it's backed by considerably more than computer simulations alone. Apollo lunar samples, brought back by 6 crewed missions between 1969 and 1972, show oxygen isotope ratios, specifically the ratios of oxygen-17 to oxygen-16, a signature that varies measurably between different bodies in the solar system depending on where and how they formed, that are startlingly, almost suspiciously close to Earth's own, far closer than the difference typically found between other pairs of solar system bodies. The Moon is also conspicuously depleted in iron and other elements that condense at low temperatures, called volatile elements, compared to Earth, which fits well with a moon built predominantly from mantle material rather than from a planet's dense metallic core, exactly what you'd expect if the Moon formed from debris blasted off Earth and Theia's outer, rocky layers rather than from their cores. And the angular momentum currently locked into the Earth-Moon system's combined rotation and orbit today matches, with reasonable accuracy, what a large, off-center, glancing impact would be expected to produce. But here is where the story gets genuinely more complicated than the simplified version most documentaries stop at, and it's a complication significant enough that researchers in the field have openly referred to it, in published papers and conference talks, as a crisis for the giant impact model. The problem is precisely that startling similarity in isotope ratios between Earth and the Moon. Detailed computer simulations of the giant impact, going back to the late 1990s and early 2000s, and refined many times since, consistently show that a large share of the material that ends up forming the Moon in these simulations, commonly somewhere between 60 and 90%, depending on the specific impact parameters modeled, should come from the impactor, Theia, rather than from Earth itself. That creates an obvious and serious problem. Unless Theia, purely by coincidence, happen to have formed from material with an isotopic composition almost identical to Earth's own, considered statistically unlikely given how much isotopic variation exists between different bodies that formed at different distances from the Sun. The Moon's bulk composition should show a detectable isotopic signature distinct from Earth's, reflecting that large Theia-derived contribution. Precise modern measurements, refined well beyond what Apollo-era instruments could achieve, have confirmed the near-identical match not just in oxygen isotopes, but in several other isotope systems too, including titanium-50 and tungsten-182, making the puzzle harder to dismiss as a coincidence or a measurement artifact. Researchers have proposed several serious, competing solutions to this crisis over the past 2 decades, and it's worth walking through the major candidates, because none has yet achieved the kind of decisive, universal acceptance the original giant impact hypothesis itself enjoys. This remains one of the most actively contested specific questions in planetary science today, even though the broader giant impact framework is not itself seriously in doubt. One early proposed solution, put forward by researchers Kaveh Pahlavan and David Stevenson in 2007, suggested that in the aftermath of the impact, the molten proto-Earth and the surrounding, still-hot debris disk that would go on to form the Moon remained connected by a shared silicate vapor atmosphere for long enough, potentially thousands of years, for isotopic exchange between the two to homogenize much of the difference that would otherwise have existed between Earth's and Theia's original material, essentially averaging out the isotope signatures before the Moon fully solidified. A more recent and considerably more dramatic proposed solution comes from researchers Simon Locke and Sarah Stewart, who in a series of papers beginning around 2017 proposed that sufficiently energetic giant impacts don't produce a relatively conventional planet with orbiting debris disk outcome at all, but instead briefly create an entirely new exotic type of object they named a synestia, a huge, donut-shaped, partially vaporized structure of mixed planetary material, spinning too fast to be a normal sphere but not gravitationally bound into a stable disk either, with Earth and Theia's material thoroughly mixed and homogenized throughout its volume before it gradually cooled, condensed, and separated back out into a reformed Earth and a newly coalesced Moon. If real, a synestia-forming impact would naturally explain the near-identical isotopes, because the mixing would have been far more thorough than in the simpler, more classical giant impact simulations. A related family of proposed solutions involves reconsidering the impact's geometry and the resulting angular momentum entirely. Researchers Robin Canup and separately Matija Cook and Sarah Stewart published papers around 2012 proposing higher energy impact scenarios, including a scenario where Theia struck an Earth that was already spinning unusually fast, with a day only a few hours long, or scenarios involving a more direct, higher velocity hit rather than the more commonly modeled gentle, glancing blow, that produce more thorough mixing between the two bodies' material and the resulting debris. These scenarios create a separate problem of their own, though. They leave the early Earth-Moon system with too much angular momentum compared to what we observe today, requiring a follow-up mechanism to bleed off the excess. The favored candidate for that follow-up mechanism is something called an evection resonance, a specific gravitational interaction between the Moon's orbit and the Sun's gravitational pull on Earth that, models suggest, could have drained away the surplus angular momentum over a few million years following the impact as the Moon's orbit gradually expanded outward to its present distance. Itself a process with independent support, since we can directly measure, using laser reflectors left on the lunar surface by Apollo astronauts, that the Moon continues to slowly spiral away from Earth today, at a rate of roughly 3.5 centimeters per year, confirming that orbital migration of this general kind is an ongoing, measurable, real physical process rather than a convenient theoretical patch. Yet another proposed solution, put forward by researchers Raluca Rufu, Oded Aharonson, and Haggai Peretz in a 2017 paper, suggests abandoning the single giant impact framework altogether in favor of a series of multiple, smaller impacts on the early Earth, each contributing a smaller debris disk and a smaller moonlet that later merged together into the single moon we see today. Averaging isotopic contributions across several smaller, independent impactors, this model argues, would be statistically more likely to land close to Earth's own composition than betting everything on one single large, impactor's material happening to match by chance. None of these proposed refinements challenges the basic, well-supported claim that a violent, early, large-body collision is responsible for the Earth-Moon system existing in its current form. The evidence for some kind of giant impact remains about as strong as it's been since the 1980s. What remains genuinely, actively unresolved, and openly debated in the current scientific literature is the precise mechanics of that impact, its exact energy, its exact geometry, whether it produced a classical debris disk, a synestia, or something else, and how precisely the resulting moon ended up so isotopically indistinguishable from the planet it came from. This is, in other words, exactly the kind of case where well-supported core idea, unresolved mechanism, applies with unusual force. And it's a good reminder that a scientific consensus around a broad framework, in this case giant impact, can coexist comfortably with genuine, ongoing, high-stakes disagreement about the details underneath it. The moon's formation left one more major physical legacy worth understanding before moving to the bombardment record it preserved: the lunar magma ocean. Models of the giant impact suggest the newly formed moon began its existence largely or entirely molten, a consequence of the enormous energy involved in its rapid assembly from hot, impact-generated debris. As that global ocean of molten rock gradually cooled and crystallized, denser minerals like olivine and pyroxene sank, while lighter minerals, particularly a calcium-rich feldspar called plagioclase, floated toward the surface, eventually forming the moon's bright, ancient highland crust, the pale regions visible to the naked eye from Earth, confirmed as genuinely ancient, some of the oldest surviving crust in the entire solar system, by radiometric dating of Apollo Highland samples. The last portion of the magma ocean to crystallize became enriched in incompatible elements that didn't fit neatly into the crystallizing mineral structures around them, particularly potassium, rare earth elements, and phosphorus, producing a distinctive chemical signature geologists call KREP, found concentrated in a specific region of the lunar surface, and used today as a tracer for reconstructing how the magma ocean finished solidifying and where its last, most chemically exotic dregs ended up. Refining the precise timeline of this crystallization process, and by extension narrowing down the timing of the giant impact itself, has been helped considerably in the past several years by new lunar samples, the first fresh material returned from the moon since the Apollo and Soviet Luna missions of the 1970s. China's Chang'e 5 mission in 2020 and Chang'e 6 mission in 2024 each returned lunar soil and rock samples from regions the earlier missions never reached, including, in Chang'e 6's case, the moon's far side for the first time in history, and dating of volcanic material from these newer samples has already helped extend and refine the known timeline of lunar volcanic activity, pushing confirmed young volcanism later than Apollo-era samples alone had suggested, and adding fresh data points to the broader chronology this chapter and the next one depend on. That same hafnium tungsten chronometer used earlier in this documentary to date Vesta's core formation has also been applied directly to the timing of the moon-forming impact itself, and it's one of the more useful independent checks available on when, Exactly. The collision happened because a giant impact energetic enough to partially remelt Earth would have also reset or disturbed the tungsten isotope signature of Earth's own mantle. By allowing previously separated core and mantle material to interact and partially re-equilibrate during the impact's aftermath. The precise tungsten 182 signature preserved in Earth's modern mantle rocks carries information about how late in solar system history that resetting event occurred. Different research groups, using different assumptions about how efficiently the impact mixed Earth's core and mantle material, have derived estimates for the moon-forming impact ranging from as early as around 30 million years after the solar system's oldest solids formed to as late as roughly 100 million years, a spread that reflects genuine, unresolved modeling uncertainty rather than sloppy measurement. The tungsten data itself is now measured with extraordinary precision. But translating a measured isotope ratio into a precise impact date still depends on assumptions about impact dynamics that different research groups continue to model differently. More recent analyses, incorporating updated solar system chronology and refined models of core mantle reequilibration, have tended to favor estimates on the later side of that range, closer to 50 to 100 million years after the solar system's birth, than the very earliest estimates once considered. But as with so much else in this chapter, narrowing that window further remains active, ongoing work rather than a settled figure, one more thread in an event that, 4.5 billion years on, is still slowly giving up its precise details to anyone patient enough to keep measuring. 129.50 Chapter 8 The Late Heavy Bombardment, a spike in the record or an artifact of where we looked. The moon's formation left behind more than a companion in Earth's sky. It left behind, quite literally, a recording device because unlike Earth, where plate tectonics, erosion, volcanism, and weather have erased almost all direct physical evidence of the solar system's earliest, most violent history, the moon has no atmosphere, no active plate tectonics, and no liquid water, meaning impact craters formed billions of years ago remain largely undisturbed on its surface to this day, layered on top of each other like sediment, waiting to be read. Between 1969 and 1972, the 6 crewed Apollo missions brought back a combined total of roughly 382 kilograms of lunar rock and soil, samples that remain, decades later, still the single richest source of ground truth data scientists have for reconstructing the early bombardment history not just of the moon, but by extension of the entire inner solar system, since Earth would have experienced a comparable rate of impacts during the same period, even though almost none of that direct physical evidence survives here. When researchers dated many of these lunar samples, particularly impact melt breccias, rocks formed when the heat of a large impact partially melts and reforms surrounding material. Using radiometric techniques, most prominently the argon-argon dating method, a striking pattern emerged. A large number of these impact melt ages clustered tightly around 3.8 to 4.1 billion years ago, rather than spreading out more evenly across the moon's full history back to its formation, around 4.5 billion years ago. In 1974, researchers Fuad Terra, Dmitry Papanastasiou, and Gerald Wasserberg published an influential paper interpreting this clustering as evidence for what they termed a lunar cataclysm, a genuine, sudden spike in the rate of large impacts hitting the moon, and by extension, the whole inner solar system, including the young Earth, concentrated within a relatively narrow window centered around 3.9 billion years ago, hundreds of millions of years after the moon itself had originally formed. This proposed spike came to be known more broadly as the Late Heavy Bombardment. If real, a genuine bombardment spike hundreds of millions of years after planet formation would demand an explanation beyond simple leftover debris gradually petering out, since leftover formation debris should decline smoothly and continuously over time, rather than surging back up long after the system had apparently settled down. And that need for an explanation is precisely what has made the Late Heavy Bombardment such an attractive, tempting target for dynamical models involving a delayed, dramatic rearrangement of the outer solar system, which we'll get to fully in our next and final major chapter. And this is a genuinely important caveat, prominent in the current research literature rather than a minor footnote. The cataclysm interpretation of the Apollo sample record has faced serious, sustained scientific challenges over the past 2 decades, and the debate is very much alive today. The core problem is one of sampling bias. All 6 Apollo landing sites, plus the robotic Soviet Luna sample return missions, are clustered within a relatively limited portion of the Moon's near side, and a substantial fraction of the impact melt samples collected across those sites are now understood to be connected, directly or indirectly, to ejecta from one single enormous impact event, the formation of the Imbrium Basin, one of the largest and most prominent impact structures on the visible lunar surface. If the tight clustering of ages around 3.9 billion years actually reflects the ejecta blanket and resulting resetting of local rock ages from that one specific, very large basin-forming impact, rather than a genuine solar system-wide surge in overall bombardment rate, then the cataclysm could be substantially an artifact of where the Apollo missions happened to land, rather than a true, global spike in impacts. Supporting this more skeptical view, studies of lunar meteorites, rocks blasted off the Moon by more recent impacts and later found on Earth, which, unlike the Apollo samples, come from random, unknown locations across the Moon's surface rather than a handful of deliberately chosen landing sites, have shown a somewhat wider, less sharply peaked spread of impact ages than the Apollo sample record alone suggests. A widely discussed 2016 paper by researchers Patrick Bohank and T. Mark Harrison argued, based on this broader body of evidence along with statistical modeling of the age distribution, that the data are also reasonably consistent with a more gradual decline in bombardment rate over time, without requiring a genuine late spike at all, essentially arguing that Apollo's geographically narrow sampling created the appearance of a sharp cataclysm out of what may actually have been a smoother, less dramatic decline. The debate has not been resolved definitively in either direction as of the most recent published research, and honest treatments of this topic, this one included, should present it as genuinely open. Some researchers continue to defend a real, if perhaps less extreme, bombardment spike, pointing to independent lines of evidence including ancient impact spherules found in terrestrial rock formations and refined dating of additional lunar basins beyond Imbrium. Others favor the more gradual decline interpretation, viewing the apparent 3.9 billion year spike as substantially, though perhaps not entirely, a sampling artifact. What both camps generally agree on is that the inner solar system, including the young Earth and Moon, experienced substantially higher impact rates in its first several hundred million years than it does today, and that at least some of the largest, most prominent lunar basins visible today, Imbrium very much included, do date to somewhere in that broad multi-hundred million year window after the Moon's initial formation. Whether that reflects a sharp, dramatic, coordinated cataclysm, concentrated at 3.9 billion years specifically, or a smoother, less eventful tail-off from the general chaos of planet formation, remains a live question. Whatever its ultimate cause, the bombardment era left a datable sequence of scars across the lunar surface that researchers have worked for decades to place in careful chronological order. The Nectaris Basin, one of the older large impact structures identified in the Apollo sample record, is generally dated to somewhere around 3.92 billion years ago. Serenitatis, another prominent basin, followed at roughly 3.89 billion years. Imbrium, the single largest and most thoroughly sampled basin, the one whose ejecta, as covered earlier, complicates interpretation of so much of the Apollo age record, is generally dated to approximately 3.85 to 3.92 billion years ago, depending on the specific study and sample set used. Oriental, on the Moon's far side and comparatively young among the major basins, is dated to roughly 3.8 billion years, making it, by most reckonings, the last of the truly giant impact structures to form on the lunar surface before the largest-scale bombardment finally tapered off. Taken together, whether or not that tapering off represents a genuine dramatic cataclysm, concentrated tightly around 3.9 billion years or a smoother decline, this sequence of named, individually dated basins gives researchers a real, physical scaffold for reconstructing the order and pace of the solar system's last major pulse of large impacts. That timing carries weight well beyond lunar geology, because it overlaps directly with the earliest window in which life is thought to have originated on Earth, and the overlap raises a genuinely debated question at the intersection of planetary science and biology. Molecular clock estimates for LUCA, the last universal common ancestor of all life on Earth today, generally place it somewhere between roughly 4.2 and 3.5 billion years ago, a range that only partially overlaps with, and doesn't cleanly precede, the tail end of the heavy bombardment era reconstructed from lunar basins. Some researchers have argued that the largest impacts of this period, striking an early Earth that may already have hosted primitive life or prebiotic chemistry, could have been sterilizing on a regional or even global scale, repeatedly resetting the chemical clock life had to start from. Others argue the impacts, whatever their destructive local effects, were never numerous or energetic enough to fully sterilize an entire ocean-covered planet, and may even have contributed useful raw material, organic compounds and volatile-rich debris carried in from beyond the frost line, that helped rather than hindered the emergence of the first living systems. Neither position has settled the matter, in part because the earliest fossil and chemical evidence for life on Earth is itself sparse, contested, and drawn from a vanishingly small number of surviving ancient rock formations, and reconciling the biological record with the lunar impact record remains one of the more genuinely interdisciplinary open questions connecting planetary science to the origin of life itself. It's a question that connects directly, whether the spike was sharp or gradual, to the story of what the giant planets themselves were doing during this same stretch of solar system history, which is exactly where we're headed next. 140, 10, Chapter 9, The Giants Go Wandering, the nice model and the reshaping of the outer solar system. The inner planets and the Moon weren't the only things still settling into their final configuration during the solar system's first several hundred million years. Out beyond Saturn, an entirely separate and, in its own way, even more dramatic story was unfolding, one that didn't happen quickly, and one that reshaped the outer solar system's entire architecture in ways still directly visible in the sky tonight, for anyone who knows where to look. The dominant modern framework for this part of the story is called the Nice model, named not for anything to do with its quality, but for the French city of Nice, home to the observatory where the idea was substantially developed, first published in a set of 3 companion papers in the journal Nature in 2005 by researchers Rodney Gomes, Harold Levison, Alessandro Morbidelli, and Cleomenes Tsiganis, and refined and revised considerably in the 2 decades since. The model proposes that Jupiter, Saturn, Uranus, and Neptune did not form in anything close to their current orbital positions. Instead, it proposes they originally formed in a considerably more compact configuration, all packed within roughly 5 to 17 astronomical units of the Sun, embedded within a surrounding disk containing an estimated 35 or so Earth masses worth of leftover icy planetesimals, extending outward to perhaps 30 astronomical units, the debris left over from the giant planet's own formation process, not yet swept up or ejected. For a considerable stretch of time after formation, potentially several hundred million years, according to the original and most widely cited version of the model, this compact configuration was stable, or nearly so, with the giant planets slowly, gradually exchanging angular momentum with the surrounding disk of icy planetesimals through repeated gravitational scattering events. Individual planetesimals passing close to a giant planet, having their orbits nudged slightly, and in the process nudging that giant planet's orbit slightly in return. Averaged over very long timescales, this produced a slow, steady drift. Jupiter crept very slightly inward, while Saturn, Uranus, and Neptune drifted gradually outward, with Neptune and Uranus's relative order to each other potentially unstable during this phase. The critical moment in the whole model arrives when Jupiter and Saturn's orbital periods, drifting slowly apart from each other throughout this process, happen to cross a specific mathematical ratio. The point where Saturn's orbital period became almost exactly twice Jupiter's, a configuration astronomers call a 2:1 mean motion resonance. Crossing this resonance is the dynamical trigger for everything that follows in the model, because a resonance crossing between the two most massive planets in the solar system doesn't produce a small, gentle effect. It produces a strong, repeated gravitational kick, timed to reinforce itself orbit after orbit, that rapidly pumped up the eccentricities, meaning the ovalness of both Jupiter's and Saturn's orbits, and through their combined gravitational influence, destabilized the orbits of Uranus and Neptune as well, essentially all at once by astronomical standards, over a span that simulations suggest may have been as short as a few 100,000 years, following several 100 million years of comparative calm beforehand. Once destabilized, Uranus and Neptune's orbits became highly eccentric and chaotic, and different runs of the simulation show the two ice giants potentially even swapping their relative order, meaning the planet we now call Uranus and the planet we now call Neptune may not have kept the same relative positions throughout this event that they'd held immediately after formation. Critically, in most versions of the simulation, Neptune's newly eccentric, unstable orbit plowed directly outward into the surrounding disk of icy planetesimals that the giant planets had been slowly interacting with for hundreds of millions of years, and this direct plunge scattered that disk violently and comprehensively. Some of that icy material was flung inward toward the Sun, adding to the population of small bodies crossing the inner solar system during this same general era. A significant fraction was scattered outward into more distant, stable orbits, forming what we now observe and call the Kuiper belt. And a further fraction was ejected onto extremely wide, weakly bound, or entirely unbound orbits, the raw material, according to this model, for the distant, roughly spherical shell of icy bodies called the Oort cloud, believed to be the ultimate source of most long-period comets, though the Oort cloud itself remains far too distant and faint for any direct observational confirmation of its structure, making this specific connection more inferential than the Kuiper belt evidence. The nice model earns its considerable influence in the field, and the reason it's taken seriously despite proposing such a dramatic rearrangement, because it doesn't just tell one story. It simultaneously explains several previously separate, previously puzzling features of the outer solar system with the same single underlying mechanism. It explains the detailed orbital structure of the Kuiper belt itself, which is not a smooth, simple ring of debris, but shows distinct, previously hard-to-explain subpopulations. A dynamically hot, more inclined and eccentric population consistent with having been scattered and stirred up during a violent instability event, alongside a dynamically cold, more circular and less inclined population, including bodies like Arakoth, which we discussed earlier, that appears more pristine and less disturbed, plausibly having formed farther out from the initial chaos and been less strongly affected by Neptune's outward plunge. It explains the existence of resonant Kuiper belt populations, including Pluto itself, trapped in stable orbital resonances with Neptune that are difficult to populate so efficiently through any process other than a genuine outward migration of Neptune sweeping through and capturing objects into resonance as it moved. And it explains Jupiter's Trojan asteroids, two large swarms of small bodies trapped at gravitationally stable points 60 degrees ahead of and behind Jupiter in its orbit, whose surprisingly diverse compositions have long puzzled researchers who expected objects formed together at a single stable gravitational point to look more uniform. Diversity, the nice model explains naturally, since it proposes the Trojans were captured chaotically from a wide range of original locations during the same violent instability period, rather than having formed quietly in place. The model's connection to the Late Heavy Bombardment, discussed in our previous chapter, was originally one of its most celebrated selling points. If the giant planet instability happened several hundred million years after formation, as the original 2005 papers proposed, it would send a wave of scattered debris sweeping through the inner solar system at right around the same time. The Apollo sample records seemed to suggest a bombardment spike had occurred, offering an elegant, unified dynamical trigger for exactly the kind of delayed cataclysm the lunar rock record appeared to show. This is, admittedly, the shakiest link in the whole chain, precisely because, as we covered in the previous chapter, whether the lunar sample record actually reflects a genuine delayed spike, or is substantially a sampling artifact from Apollo's limited landing sites, remains itself an open, unresolved question. If there was no true late spike in bombardment to begin with, the nice model doesn't need to explain one, and more recent revisions to the model, sometimes referred to informally as early instability variants, have explored giant planet migration happening considerably earlier, within perhaps the first 100 million years after the disk's dispersal, rather than several hundred million years later. Partly in response to these ongoing questions about the true timing and reality of the bombardment spike, and partly in response to separate concerns that a very late instability might have been dynamically disruptive to the terrestrial planet's orbits in ways inconsistent with their observed present-day stability. The original 2005 NICE model also ran into its own separate, purely dynamical problem, once researchers tested it more rigorously. In many simulation runs, the resonance crossing event left Jupiter's final orbit more eccentric than the real, observed Jupiter's orbit actually is, and tended to overexcite the orbits of the inner terrestrial planets in ways inconsistent with the comparatively calm, nearly circular orbits Mercury through Mars display today. This led to a significant refinement published by several of the same researchers around 2011, sometimes called the jumping Jupiter variant, in which the instability proceeds not through smooth, continuous migration alone, but through one or more close encounters between Jupiter and one of the ice giants, Uranus or Neptune, that gets gravitationally scattered inward and then flung back outward again, causing Jupiter itself to shift, or jump, somewhat abruptly in its distance from the Sun rather than migrating smoothly, an outcome that better matches Jupiter's actual, more circular present-day orbit, and does considerably less collateral damage to the inner solar system's terrestrial planets in the process. This jumping Jupiter refinement is now generally considered a more accurate version of the underlying instability model by most researchers actively working in the field, though, as with the broader question of instability timing, the precise number and identity of which ice giant or giants were involved in these close encounters, and the exact sequence of events, remains a subject of ongoing simulation work and continued refinement rather than a fully settled question. Taken together, the broader migration story, giant planets forming compact and migrating apart, driven by interaction with a surrounding disk of icy debris, followed by a comparatively rapid dynamical instability once a resonance was crossed, has strong, independent support from orbital dynamics, from the detailed structure of the Kuiper belt, from the Trojan asteroids' compositional diversity, and from the broader statistical demographics of giant exoplanet systems around other stars, many of which show orbital configurations that are difficult to explain without invoking some form of post-formation migration having occurred. What remains less certain, and remains an active area of published, ongoing scientific debate, is the precise timing of the instability event, exactly how it connects, if at all, to the bombardment record preserved in lunar rocks, and the exact dynamical sequence, which planets encountered which, in what order over what precise span of time, that carried the outer solar system from its tightly packed birth configuration to the widely spaced arrangement of Jupiter, Saturn, Uranus, and Neptune we see and rely on tonight. The instability's reach extended even into the giant planet's own family of moons, and one satellite in particular carries what may be the clearest single fingerprint of that chaotic era still directly observable today. Neptune's largest moon, Triton, orbits backward retrograde, opposite to Neptune's own spin direction, and on an orbit steeply inclined to Neptune's equator, a combination essentially impossible to produce through the normal, orderly process of a moon forming alongside its planet from a shared disk of material. The leading explanation is that Triton is a captured object, most likely a large body originally belonging to the same primordial disk of icy planetesimals that the nice model's instability scattered so violently, pulled into orbit around Neptune sometime during or shortly after that chaotic period, when close encounters between Neptune and other large bodies were common enough to make gravitational capture, ordinarily an extremely unlikely event, plausible. Consistent with this origin, Triton's density and surface composition, including confirmed nitrogen and methane ices, and active geysers observed directly by Voyager 2 during its 1989 flyby, resemble Pluto's more closely than they resemble any of Neptune's other, presumably native moons, supporting the idea that Triton began its existence as a large, independent Kuiper belt object before Neptune's gravity claimed it during the general upheaval this chapter has described. Jupiter and Saturn's own satellite systems carry a fainter, more diffuse version of the same signature. Beyond each giant planet's small set of large, regularly orbiting moons, formed in place from a planet's own miniature disk, the same basic process that built the Sun's disk on a larger scale. Both planets also host dozens of much smaller irregular satellites, following distant, often highly inclined, sometimes retrograde orbits that, like Triton's around Neptune, are difficult to explain through orderly in situ formation. These irregular moons are widely interpreted as captured objects, gravitationally snared from the surrounding population of small bodies during the solar system's early dynamically active period, plausibly including the same instability event described throughout this chapter, when close encounters and gravitational perturbations were common enough to make capture far more likely than it would be in today's comparatively settled, well-ordered solar system. Their orbital groupings, several of which cluster into distinct families sharing similar orbital inclinations and distances, hint that at least some of these moons may be collisional fragments of larger captured bodies that broke apart sometime after capture, adding yet another layer of collisional history sitting quietly in the outer solar system's satellite catalogs, still being sorted out today through continued ground and space-based observation, including targeted surveys specifically designed to hunt for additional small, faint, irregular moons still awaiting discovery around all four giant planets. The nice model, in its various refined forms, still doesn't explain everything. Some researchers, including Harold Levison, David Nesvorny, and collaborators, have proposed in a series of papers beginning around 2011 that the solar system may originally have hosted a fifth giant planet, roughly ice giant-sized, alongside Jupiter, Saturn, Uranus, and Neptune, which was ejected entirely from the solar system during the instability's most chaotic phase, ejected far more easily than any of the four surviving giants, absorbing a large share of the encounter's total energy and angular momentum in the process, and thereby helping explain features of the surviving system, including Jupiter's relatively mild final orbit, that are difficult to reproduce cleanly in simulations using only 4 giant planets from the start. No direct evidence of this hypothetical fifth planet survives, by definition, since an ejected planet becomes an unbound, untraceable rogue world drifting the Milky Way indefinitely, and the idea remains a proposed refinement rather than an established feature of the model. And the outer solar system has at least one remaining, unresolved oddity that some researchers connect, speculatively, to this same general era of gravitational upheaval, or something like it happening even farther out. Sedna, a small, distant world discovered in 2003, follows an extraordinarily elongated orbit that never brings it anywhere near Neptune's gravitational influence, a detached orbit that standard nice model scattering struggles to produce on its own. Proposed explanations range from a close passing star disturbing the young solar system's outer edge, to an as yet undetected distant planet, the modern, still entirely unconfirmed Planet 9 hypothesis, gravitationally shepherding Sedna, and a handful of similarly detached objects into their unusual orbits. This is speculative territory, clearly flagged as such by the researchers proposing it, and stands as an honest reminder that even after everything this chapter has covered, the outer solar system's full dynamical history, 4.5 billion years on, still isn't a fully closed book. 154.30, Epilogue, where this leaves U.S. added up in order, the way it actually happened. A cloud, sitting quietly for a long stretch of time, gets disturbed, possibly by a nearby supernova whose isotopic fingerprints are still detectable in ancient meteorites today, though the details of that trigger remain genuinely debated among the scientists who study it. The disturbed fragment collapses and, because it was already very slowly rotating, spins up and flattens into a disk, for reasons of angular momentum conservation as rigorously demonstrable as any principle in physics, and we can watch equivalent disks being born around other young stars today with instruments like ALMA. A star ignites at the center of that disk, takes over gravitationally, and eventually clears away almost all of the leftover gas through its own wind and radiation, in a process directly observed happening to other young stars across the galaxy right now. Dust grains claw their way up toward planetesimal size, crossing a genuinely unsolved barrier that current research increasingly credits to something called the streaming instability, a process with direct physical support from a small, gently fused world a billion miles past Pluto. A frost line splits the disk cleanly into a rocky, metal-rich inner system and an icy, gas-rich outer one, giving rise to 2 entirely different categories of planet from one single underlying temperature threshold. Protoplanets collide and merge in a demolition derby that, for Earth specifically, ends with a Mars-sized world slamming into the young planet and leaving behind not just a moon, but a genuine, unresolved scientific puzzle about why that moon's chemistry so closely matches Earth's own. That same bombardment-scarred era gets etched into lunar rock, in a pattern that may or may not represent a sudden, dramatic spike in impacts hundreds of millions of years after formation, a question the Apollo samples alone still can't fully settle. And finally, long after the inner solar system's dust had mostly settled, the giant planets themselves went wandering, crossing a critical orbital resonance that kicked the entire outer solar system into a new configuration, scattering 1 trillion icy bodies into the dark, seeding the Kuiper Belt and possibly the Oort cloud, and only then, after all of that, finally settling into something resembling the solar system you'd recognize if you looked up tonight. None of that sounds like the recipe for a calm, stable, 4-billion-year-long stretch of relatively boring, predictable orbits, the kind of long, undisturbed stretch that gave a rocky planet with a large, stabilizing moon enough uninterrupted time to let chemistry slowly become biology, and biology slowly become you, reading or listening to this sentence right now. But that's exactly what came out the other side of all of it. The chaos didn't get cleaned up afterward, as some kind of messy preamble to the real story. It was the process. The collisions, the migrations, the resonance crossings, the near misses that didn't quite happen, the isotopes still faintly detectable in 50-year-old meteorite fragments sitting in laboratory drawers. None of that was an obstacle the solar system had to overcome on its way to stability. It was the actual mechanism that produced the stability, the same way a demolition derby, rather than being the opposite of an orderly outcome, is in this specific and literal case exactly how the orderly outcome got made. It's also worth being honest, one final time, about how much of this story is still being actively written. The supernova trigger, the precise mechanism behind the meter-sized barrier, the exact geometry of the moon-forming impact, the reality and timing of the late heavy bombardment, the fine details of the nice model's instability. These aren't settled textbook facts being simplified for a general audience. They're the genuine, current, published frontier of planetary science, argued over in real journals by real researchers using real spacecraft data, real meteorite samples, and real supercomputer simulations, revised as better evidence arrives, the way all good science eventually is. That's not a weakness in the story. It's what makes it a true story rather than a myth. Myths don't get revised when a new isotope measurement comes in from a lab in Chicago, or a new spacecraft flies past a small icy world a billion miles from home. Every stable orbit you could point a telescope at tonight is a survivor of everything this video just walked through. 4.5 billion years compressed into 2 hours of narration, but representing an amount of actual time so vast it's genuinely difficult for a human mind to hold onto with any real intuition. Next time you look up at a calm, quiet, unmoving night sky, it's worth remembering that you're looking at the settled wreckage of a much louder history. A cloud that didn't have to collapse, a disk that didn't have to flatten the way it did, a barrier that dust somehow, still not fully understood, managed to cross, a collision that shouldn't have left a moon so chemically identical to Earth, and a quartet of giant planets that spent their early history wandering rather than sitting still. All of that had to happen, roughly the way it happened, more or less in the order it happened, for there to be a stable enough platform, held together for 4 billion undisturbed years, for anyone to ever be around to look up and wonder about any of it at all.